Is better? Right. So again, I want to ask every student, hope everybody can hear me, can listen me properly, and there is no problem in the audio. Video we have stopped, okay? In the beginning I asked, and the student mentioned, yeah, it's quite clear. Again, I want to ask. So the moment I put a question, that time you should unmute your mic, okay? You should reply.
Yes, sir.
Okay, right. There should be at least one student, okay? Maybe the CR, if the CR is the class representative is present, so he's the one, okay, to reply, okay? When I ask, for example, any problem, or for example, in communication or in audio or in maybe sometime video, so instead of all, the best is if CR is there, okay? For example, CR number 1 is not there, hope you got an alternate CR, okay? So then he or she might be the one to respond, okay? Okay, good to see you again. Assalamu alaikum, good morning again to everybody. Let me share the screen, okay? So I want to go for sharing. When it is available, then you tell me, okay? When the slides are available on the screen, then you tell me, okay? Okay, nobody is allowed to enter outside UT, because I got one message. Someone from outside university is trying to join, okay? So it's only for UT Peshawar, okay? Mechanical department, because you are having the UT email IDs, and using those email ID, you can log in. So it's your responsibility not to share with other, okay? This link, because the problem will be, although the notes are available, everybody, whether it is student of UT or any student, notes are available online. He or she can download the notes. You can share with any student, okay, to get benefit of. But this time, because we want to make sure there will be no connectivity, okay? So anybody who knows who is M. Bilal Amir, because this is the message again I'm getting. M. Bilal Amir outside UT Peshawar is requesting to be admitted. Is it from your class? CR M. Bilal Amir. CR. Anybody?
No, sir. No, sir.
No, so you should be very much proactive, okay? You should be very much proactive, okay? You should be loud. The time you are responding, you should be loud, okay? You are gentlemen. You are not old people, okay? You are healthy gentlemen, okay? You should be very much proactive, very much loud the time you are responding. I want to ask, who is M. Bilal Amir? Does he belong to your class section?
Sir, we don't know him, and the CR is
Okay.
absent, so.
Right. So, okay. No. Okay. Because it is second time I got the message that he want to join the class, and then I denied. Because the connectivity problem, okay? The connectivity problem, if we allow other people outsider, why we should allow outsider? Because the number of students will increase, so maybe there is a connectivity problem, okay? So when slides are available on screen, you please tell me, okay?
Yes, sir, we can see the slides, sir.
Okay. Very good, Shabash. Okay. So I just want to maximize. So these are the slides already I have provided, okay? Sometime after I upload the slide, then maybe some minor refinement I do, okay? The rest everything is the same already, but because it is my notes, okay? I have uploaded. So sometime after I upload, and then when I go through, somewhere I fine tune, okay? Maybe at some 1 or 2 slides, okay? So, okay. Okay, dear students, so basically, today is lecture number 5, but if you look into the slides I have downloaded, it's not a new topic, okay? Because you remember, it was, I think, second week of March when this break happened, okay, because of COVID-19. And more or less, if you can't, so more or less 2.5 months you are out of classes, okay? So I thought that if I start from a very new topic in this lecture, it may be hard for you, okay, to understand. So I would like to give an overview, or you can say a revision of the previous lecture that we have delivered in the classroom during face-to-face teaching, okay? Because these are the fundamental things, these are the basic things, okay? And the basic, the fundamental for every subject, once you understand, then the rest of the lecture, the rest of the concepts become very simple and very easy and very convenient for you to understand, okay? So basically, today what I will deliver today, what I will teach, so So these are things already I have taught, okay? But just for the sake of revision, so that it is fresh, okay, to your memory, okay? It is fresh for you all, okay? And then everybody is in the position, you are everybody capable to understand in future coming lecture, okay, and the content, okay. So for this particular purpose, I just decided that we should go for some review, or you can say overview, or you can say the revision, okay. So everybody knows the topic of the title of the course is Mechanics of Material 1. It is the part 1 which will be taught, or which is being taught in this semester 2. Already I have mentioned second part of this course will be Mechanics of Material 2, which you will inshallah learn, and inshallah I will teach in your semester 3, okay, next semester. So just I mentioned it's a revision 1 class, okay. And again, if you look into the previous slide, the previous lectures what I have taught, so basically you can find lecture 1 and lecture 3, okay. They were basically lectures, and lecture 2 and 4 they were basically tutorial, okay. Because in these lectures what I did, we went for solving problem, okay. They were relevant to lecture 1 and lecture 3. So I don't want to go for revision of the tutorial. I just want to go for giving overview of the lecture, the topics, okay, the fundamental, the basic things, okay. Because once you understand the basics, then problem solving is not a problem, okay. So first we will start from overview of the previous lecture 1, and if you look into the date when it was delivered, okay, first time, so it was basically the last week of February 2020 when your first lecture, okay, was scheduled in this week, okay. So it is now you can say first week of June, so you can look into the break, okay, the gap. Okay, so basically in this something about the course contents already I have explained in the classroom, okay, and again I have provided in the slide, so no need to go for explanation because these are just the content, or you can see the topics, okay, which will be taught in this course, or these are things we will go to learn in this topic, okay. We can have a look up, okay, and then there is no need to
The screen नजर नहीं आ रहा.
I asked to mention it, you can see it. I asked you people, you mentioned, yeah, you can see. So everybody can see.
Screen नजर नहीं आ रहा sir जी.
No, sir.
No,
There
but
is
when
no
I
screen.
No sir.
when I shared, so I asked you people and you mentioned, yeah, we can see. Okay, let me try again. No worry, okay. So I want to share. So
थोड़ा
I
zoom
want
करो,
to
फिर नजर आता है थोड़ा zoom.
okay, so it is asking resume presenting the screen, okay, presenting the lecture. Hope you can see it after a few seconds.
Yes, sir.
You can tell me again.
नजर आ रहा है. Yes, sir. We can see.
Okay. Okay. Right. Okay. Good. It's good. Okay. Whenever there is some problem, because I don't know. Okay. Once I share the screen and you ask me it is there, then I will start the teaching. Okay. But at any moment, if some problem happens, okay. So the best is you let me know. Okay. For example, you cannot hear me, or for example, there is the screen not shared. Okay. Then because I don't know what was the reason, but initially I shared, but then what happened? You couldn't see it. Okay. So let me again maximize so that you can see it properly. Okay. So basically course contents, I mentioned, I don't want to go for explanation. These are only the topics which you will be learning and I will be teaching, okay? And then the intended learning outcome for today's lecture, because if you remember in the first lecture I have mentioned that it is very much important that for every lecture, the student must know in the very beginning of the lecture that what are some things they are expected to understand from the lecture, okay? So these are things, okay? You can say that, for example, since this is the lecture 1, so basically the introduction type of thing we have put in the beginning, okay? Like for example, you should know the course content and then the recommended books, okay, and the mass distribution, CLO, PLO type of thing, okay? Because CLO for the course are important and its mapping with the PLOs are important. And in the classroom, you remember in first lecture, there is a quite big detail, okay? Detailed discussion has been made. And then there should be some end objective of the application of the subject, because you should know where this subject you can apply, okay, what are the areas of application, what are discipline, okay, what are the disciplines where you will be required to apply this subject of mechanics of material, okay. And then we will start for some formal teaching that starting from load, for example, what is axial load, normal load, shearing load type of thing, and then stresses with some example and some maybe numerical solution, okay. And the books, you remember in the lecture 1 in the class, I have mentioned a number of books are there, okay? There are some textbook in the beginning, I have put 1, 2, 3, and then there are some reference books, okay? 3 books are for reference books. And already I have mentioned for every lecture in advance, you will be having through Google Classroom, the lecture slides, okay, PPT or maybe PDF. So already I give, okay, no worry. But again, I have advised you quite before that it will be good that you go to the library, or maybe you can search online. So one of these books, all are good books. Okay, I cannot say this is good and this is not good. No, these are all books. These are all relevant books to the subject, which is mechanics of material. It's upon you, okay, which book you like the most, okay, depending upon your sense of, okay. Some people go for example, simple English. Some people go for good quality of picture, etc. Okay, so you are the one to decide. But my advice as a professor, as a teacher, would be at least one of the books, okay, whether the top 3 or the bottom 3, you go to the library or you search online, and then you must read it, okay, along with the slide I am providing. It will be something good for your more learning. And then again, I don't want to go into discussion, but the only thing I want to mention here is in the mass distribution, because for sure there will be some quizzes. Already I have mentioned in the lecture 1, okay, in the face-to-face lecture, there will be some assignments, okay, midterm, final term, okay. But now since things are changing, okay, because of this COVID-19, and again, everybody should pray. This pandemic will be over quite soon, okay, and then we will be in the face-to-face classes, okay. But as long as it is there, so there may be some changes, okay. We are not yet sure, okay. For time being, we can say sessional will be 30 instead of 20, because in the current, if you look into, so one change we have brought, okay, and that is the sessional, which was previously 20, now they will be 30. Why 30? Because previously the weightage was 60, okay, for final exam. But now, because of this one, to give you a favor, okay, basically it is reduced from 60 to 50, okay, and the 10% will be given to sessional, okay, and the sessional will be for quizzes and assignment. So basically 30 will be the sessional, 20 midterm, and then 50 the final, okay. And again, midterm exam, what will be the mode of midterm exam? Once inshallah we move ahead, and then for example a week before the midterm, then we will decide what is the for example mode through which we can conduct the mid exam, okay, later on. Attendance, already you know, it is something a requirement. So this is very important, quite detailed discussion I have made in the lecture, because basically you are alhamdulillah going through OBE type of teaching, okay, and learning, okay. So outcome based teaching and learning. So there is a requirement of CLOs for every subject, and PLOs, achievement attainment, okay. So every subject CLO and PLO of the program you should attain. So there are 12 PLOs. If you remember, we have displaced in the department at various places. Everybody should know, okay, what are the 12 PLOs, starting from PLO number 1, which stands for program learning outcome, up to PLO 12. So these are the minimum which are provided by HEC, okay. We can make it more, but the time, these are only 12, okay. And for every course, whether it is solid mechanics or fluid mechanics or thermodynamics or English, for example, or presentation or CAD, etc. So there are some CLOs, and CLO, you remember we have discussed, this stands for course learning outcome, meaning that at the end of a particular course, what are something the students are expected to have learned, okay. Because once you spend one whole semester, more or less 18 weeks of teaching, okay, and then at the end, what is something you should be having, but you must have learned, you must have understood, okay. So that is the expectation, okay, and that we put in the category, we call it CLO. So basically there are 3, you can see. Number 1 is to understand the basics of mechanics of material and their mechanical properties, and the second is to calculate the stresses and strains in mechanical properties, and the third is to solve problems related to bending and torsion in mechanical structures, and they belong to the domain of cognitive taxonomy level. You can see 1, 2, 3, and then number 1 CLO of this course is related to PLO number 1, and second and third CLOs, they are related to the second PLO of the program. So little discussion which already we have made, because it is a review, so no more not very much discussion, but little discussion as an overview, okay. What is mechanics? That is basically, if you remember in the classroom, I mentioned that every student have gone through metric and FSC, and there you are studying science subject, okay. In science subjects there were mathematics and physics and chemistry and biology. Okay, so basically in physics, then mechanics is a subtopic. Okay, so mechanics is something, a discipline, an area which belongs to physics, and physics is something which belongs to science. Okay, so basically mechanics is something important for engineering students, especially mechanical engineering student, and also for civil engineering student. So what is mechanics? Basically mechanics is the branch of science which describes and predicts the conditions of rest or motion of bodies under the action of forces. So basically there are two things in mechanics. Okay, one is the body, and then there is a force. Okay, so if there is a body but the body is not subjected to some force, so there is no use to talk about mechanics. Okay, but if there is some force but the force is not applied to a body, again no use of mechanics. Okay, so once there is a solid body and that solid body is subjected to external force, then that time you will be expected, okay, that you should apply your role as a student of mechanics. Okay, and again when we say body, so body, you remember we have classified it into two types. One of the type of the body we call, you remember, rigid bodies. Okay, and the second type of the body we call non-rigid bodies, or you can say deformable bodies. Okay, so rigid body, what was the definition? You remember the simple definition we provided in the lecture 1 last time. So those bodies which when you subject to external forces, and because of the forces the bodies are not changing their dimension or their size or their shape. Okay, so they are called rigid bodies. Okay, you applied external load, but because of that load the body is bringing no change in dimension or in the shape, so that body will be called rigid bodies. Okay, and under this rigid bodies, basically in your mechanical curricula there are two subjects. I think one of the subject already you are taking, and that is engineering statics. Okay, because in this engineering statics, okay, the body is assumed to be rigid, and then once you apply force, okay, so you want to know the behavior of the body. Okay, what is the behavior of the body, what is the response of the body, what is the reaction of the body once it is subjected to some force, but that body for sure will remain in state of rest. Okay, the other subject under this category will be, I think, maybe semester 3, that will be called engineering dynamics. Okay, where the body will be in motion. Okay, when you apply force and then the body is moving, so maybe you are interested in what is the velocity, or for example the acceleration of the body. So under rigid bodies, already two important subjects in your mechanical curricula are engineering statics and engineering dynamics. Okay, the other type of or category of body which is called non-rigid bodies, or which is called deformable bodies. So basically there are subjects, you can say, solid mechanics and fluid mechanics. Okay, and solid mechanics, you remember I mentioned that basically solid mechanics was the old name or old title of this course, which now we call mechanics of material. Okay, so previously we will call it solid mechanics. So there are different terminology I have explained in the classroom first time. Okay, like solid mechanics you can call, mechanics of material you can call. There could be another title, for example, strength of material, or there could be, for example, another title or terminology, you can call it strength of structure or mechanics of structure. Okay, so these all more or less mean the same. Okay, so in solid mechanics or in mechanics of material, you will assume the body to be deformable, meaning when you apply load to that body, so the body will deform. Okay, the body will deform as a result of a load application. Similarly, in fluid mechanics, the body will be, the fluid is deformable. Okay, now mechanics, so because of the importance, we can say mechanics is the foundation of most engineering sciences and is an important prerequisite to this study. So how we will define in simple word mechanics of material or solid mechanics? So basically mechanics of material is that branch of mechanics which is dealing with the internal effect, or you can say internal response. Okay, or you can say the reaction. Okay, which we call it a stress and strain, which will be produced in the body when you subject to external force. Already I mentioned, okay, that basically in mechanics of material there are two things. Okay, there should be a deformable body, and that deformable body you should apply, or you should subject to external load. Okay, so when the body is subjected to external load, so you know it will be under stress. Okay, so the applied load will produce stress in the body. This is confirmed. So stress is an important quantity you will have to deal, whether it is mechanics of material 1, it is mechanics of material 2, it is design. Okay, so very important quantity. Okay, so you will have to deal with stress. Okay, so whenever a solid body is subjected to load, that load will produce stress. So stress an important quantity. Okay, which you should know. Okay, and then at the same time you can say that when you apply external load to a solid body, so the solid body will deform. You can say strain will be produced in the solid body. Okay, so strain is another important quantity you should know. Okay, whether it is mechanics of material part 1, 2, or it is machine design part 1 or machine design part 2. Okay, so these, remember, stress and strain are very important quantity. And as a student of mechanical engineering, or in future, inshallah, as a good designer, or for example, mechanical engineer in future, when you are, inshallah, after graduation, working in some field. Okay, and there is, for example, let's say design section. Okay, then these are important things you will have to deal all the time. Okay, because basically all the structure, okay, all the bodies, okay, for example, machine element, machine element we have explained, okay, like shaft, gear, bearing, key, spring, these are all mechanics element. Okay, so these all elements are subjected to external load, and because of external load, there are two things: they are under stress, so how to calculate the stress, and also there is strain produced in these components, so how to produce or how to calculate the strain. So if you remember, I have mentioned that it is not only for mechanical engineering student this subject, this is equally important for civil engineering student as well. Okay, because civil engineering students, they are studying also structures. Okay, building structures, you can say highways, bridges, so those are also solid bodies, and they are deformable bodies. Okay, whenever there is a bridge, okay, and the bridge is subjected to external load because of a number of, for example, you can say cars or automobiles, okay, or traffic. Okay, so it will be under load, and because of that load, there will be stress produced in the bridge. Okay, and you will have to calculate, or the civil engineering students are required to calculate what is the stress which is produced in the structure. For example, maybe column, maybe this bridge. Okay, and again there will be strain produced. So how much it is important for you, this subject, you mechanical engineering student, equally it is important for civil engineering students. Okay, so now remember, when we say these are two important things, so from the very beginning, even in the first lecture when we were in the face-to-face teaching, I have stressed very much on these two things. Okay, that these are basically very important things, and from very beginning you should have a clear understanding of these two quantities. Okay, now stress, stress you will have to calculate. Okay, in onward, for example, calculation, or maybe lectures or problem solution. So stress, okay, stress, which we say an important quantity. So this is associated with strength of the material of which the body is made, because every part, every body, every product is made of some material. Something is made of wood. Some bodies are made of plastic. Some are made of steel. Okay, so there is a material, and every material have a strength. Okay, so stress is something. It is associated with strength of the material. And the other quantity, which is strain. So strain is something which is associated with deformation in a body. Okay, so once a deformation is produced, using the deformation, you can calculate the strain of the body. So apart from this thing, a little discussion with respect to the applications of the subject, which is mechanics of material. Meaning you should know what are the areas, what are the disciplines where this subject, or the knowledge, or the concept, or the fundamental, or the theories of this subject could be utilized. Okay, so you can see a number of areas, starting from mechanical engineering, civil engineering. Already I mentioned, okay, that it is equally important for civil engineering. Okay, and then aeronautical engineering, geomechanics, okay, manufacturing, biomechanics. Biomechanics, this is something an emerging field in Pakistan, more or less for the last 5, 6, 7 years. It is emerging. Okay, something good field. So basically, what is basically in this field? Designing implants. Okay, implant, okay, so implant is again a solid body, and this solid body, when you put in the human body, okay, so it will be subjected to external load, and then there will be stress is produced, and maybe there is deformation. So all the theory what you can apply to, for example, other parts, or maybe machine element, those theory you can apply to design of implants. Okay, what is the material you will have to select, okay, for that implant? What are the dimensions, for example, you have to select for the implant, okay, etc. And then you can say material science and microelectronics, nanotechnology type of areas are there where you will need the mechanics of material application. So very important, and you can say a very important, or a core subject. Okay, a core subject of mechanical engineering curricula, this subject, which is mechanics of material, apart from other subjects like design and thermodynamics type of thing. Okay, so you should have a very good understanding. Okay, and it is very simple and very easy to have a very good understanding and learning of this subject, or the topics of this subject. Okay, provided you are punctual. Okay, you are regular to take the classes, okay, or you are taking some interest, okay. Now, somehow with respect to load, with respect to force, okay. So basically, again, a number of force types we will discuss in the class, okay. We start here from, in the overview, from normal force, okay. So basically, normal force we can see in the figure, okay. One is the figure on the left side, one is the figure on the right side. So normal force, basically the name shows normal force, meaning it is a force which is normal or which is perpendicular to the face or to the section, okay, to which it is acting, okay. Like in the left side, you can say the okay, the small rectangle, okay, on the left side, on the right side, the small rectangle. So this small rectangle basically shows the cross section, or you can say the section, or you can say the plane, okay, the plane to which the force is acting. So if it is the left figure or it is the right figure, the force direction is normal to the plane, okay. So this is xy plane. So therefore the force we call normal force, okay, for the simple reason that it is acting normal or perpendicular to the plane. Now when it is normal, then you can see from the figure that the direction of the force may be either toward the plane or it may be away from the plane. So when you can see in the left figure, the direction of the load is towards the plane, then this normal force you will call compressive force, okay, compressive force. And when the direction of the force is away from the plane, then this force we will call tensile force. And you should know, okay, and it is very much clear that whenever you apply force, okay, any type of force, when you apply, so there will be some effect of that force. So what is the effect of the normal force? You can see, okay, in the slide. So basically on the left side, if you look into the force, which is compressive force, so the effect of compressive force is it will tend to shorten the part at which it is acting. It will reduce the length. It will reduce, okay, it will shorten the member to which the compressive load is applied. What is the effect of tensile load? So you can see when you apply tensile force to a bar or to a member or to a body, so the effect of tensile force will be to elongate, to increase the length of that body, okay. So this is the effect of the force. Okay, again I just want to confirm every student is online. I can see from the people, okay, and hope everybody can listen properly. There is no problem in the audio.
Yes, sir.
Yes,
Good.
sir.
Okay, very good.
Yes,
Okay, very
sir.
good.
Yes, sir.
Right. Good. Okay. Then when we say normal force, so whenever there is a force, so there will be stress for sure. When it is normal force, so I don't want to go into more detail because already this is the lecture I have delivered, okay, in the face-to-face, just an overview, okay. So normal force we mentioned, okay, what is normal force from the previous slide. And whenever you apply normal force to a body, you can see in the figure, okay, on the left side, part A. So here is the force, you can see from the figure, it is acting normal to the cross section, okay. So this normal force will produce normal stress, and normal stress you can see we represent by a symbol which we have called sigma. It's a Greek letter, okay, sigma. So sigma is a symbol we have reserved for normal stress, okay. Now you can see here what already we have explained in the lecture, that basically we consider a small differential element having differential area which we represent by del A, okay. And this differential element is offering, or it is giving a differential force, and that differential force we represent by del F, okay. So here in this case, if you look into, there is one downward force you can see in part A, that is P bar. So here is something very important you should know, because if you remember during lecture when I was telling about the forces, so I mentioned in forces then there will be two forces with respect to body, okay. One is the external applied load, and one is the internal resistance or internal force from within the body. If you remember in the first lecture, I mentioned the example of the chair, okay, the study chair when you are using in the classroom to sit in. So there I mentioned the body weight of the student on a chair is external applied load on a chair, okay, and the chair is made of some material and it has got some dimension. So the material of the chair is supporting your body, okay, or it is supporting your body weight. So there is some force, there is some reaction, okay, from within the chair, and that reaction we call internal force or resistive force. So in this case, basically, if you look into the force which is P bar, so P bar here is the external applied load, and the resistive force is here del F. But remember, this del F is not the resistive force by the whole body. It is the resistive force only by a small segment or a differential element del A of the body. You can similarly split this cross section, this whole cross section, you can split into number of differential element, okay? And each differential element will have some area del A, and each differential element will give some differential force del F, okay? So the total resistive force which will be given by this body will be basically sum of the differential forces which are given by each and every differential element of the body, right? Now coming to the point, what already we have defined the stress. Again, you can see here in the equation and the formula that since force is normal, so stress is normal, and stress already we have defined it is load per unit area. Since here the stress we define for the differential element, so the force is del F and the area is del A. And here you can see the limit del A approaches to 0, meaning del A, which is the differential area, that is so small that it is nearly equal to 0. So why we put the limit del A equal to 0 or approaching to 0? This is for the reason you can see in part B of the figure, okay? So basically stress is something we define at a point. So stress is defined at a point, and point is a dimensionless quantity, okay? So basically that is the reason we put limit del A approaches to 0. And the figure part B can show you, okay? You can see a number of arrows are there, okay? These are the arrows, okay? And each arrow is from a different point. So it is point 1, stress is this much. It is another point, stress is this much. And similarly another point, this is the stress, okay? This is another point, and you can see a number of arrows, and each arrow is initiating from a particular point. So the important point you should remember, you must remember, is stress is always defined at a point, okay? So that's why we take del A approaching to 0. And if you remember in the class, we have mentioned that this stress could be average stress, and this average stress will be equal to load applied divided by area. So this is basically here the load, okay? This P, okay? The external load, or this could be the resistive force, okay? Because external load and resistive force, they are equal in direction and opposite in equal in magnitude and opposite in direction. And this A, now this is the area of the whole cross section, okay? This A and this del A. So del A here means basically area of the small segment or differential element, but A means area, okay? This area of the whole cross section, so you can calculate because width is given and thickness is given, so it is very simple to calculate area. But if you remember in the class, we have mentioned that this equation which shows average stress, okay, and the average stress is also shown in the figure part B, okay? This is, okay? So basically it is uniform stress distribution, okay? Because if you look into the length of arrow, so from every point an arrow is emerging, and if you look into the length of each arrow, so all arrows have got the same length. So it means that at every point of this cross section the same stress is there, okay? This is the simple meaning, okay? So you can say, in other words, it is uniform stress distribution. So in the classroom we have mentioned that stress could uniformly distributed across a cross section provided 3 conditions are met. And one of the 3 conditions was that, if you remember, that the load must act or must pass along centroid of the body. So if you look into part B of the figure, so the load which is P bar, it is acting along centroid. Everybody has got a centroid, okay? Every body. So this is the load you can see, and it is the load which is acting or passing along centroid. Second condition was that the material of the body should be homogeneous, okay? That the material properties should be the same throughout the length of the body, okay? And the third condition was that the cross-sectional area, okay, this is A, the cross-sectional area. So the cross-sectional area of the body should be the same throughout length of the body. So you can see, okay, at what point you take a section or cross-section, so you will be getting the same area, okay? So if these conditions are met, and you can see all these 3 conditions are meeting here, okay, in part B of the figure. So in that case, the stress you can see will be uniform, and you can apply that stress is same, which is average stress, and that is equal to the applied load divided by cross-sectional area. At the bottom you can see there is an equation. So basically what is this P? So basically P is the load, okay? This is the external applied load, or it could be the resistive load, okay? Let's say P bar is the external applied load, then P should be the resistive force, okay? And resistive force equal to area, stress into area from this equation, okay? From this equation you can see From this equation, this load will be equal to stress into A. Now, you can say, okay, stress into area is basically force, okay, is basically force. But here we take sum of the forces, but already I mentioned, okay, that basically the resistive force, which is P, which will be given by the whole body, will be the sum of the differential forces which are given by each differential element of the body. So then you put from this equation, okay, you put the value of Tf, so it will be sigma into dA. So this is how you can calculate the normal stress which will be produced in a body as a result of application of normal force. The normal force we can see here is tensile, so the stress will be tensile stress, or this force may be compressive, and in that case the normal stress we will call compressive. So simple, the approach is we put plus sign for tensile stress, and we put minus sign with the magnitude of the stress to show that the stress is compressive, and it is because of compressive load. The unit already you know, okay, from the slide, that basically stress is force per unit area. It is basically force intensity. So force is having unit of Newton, and area is having unit of square meter. So the unit of stress will be then Newton per square meter, or it will be pound per square inch in the other system of units, okay. And already we have mentioned that 1 Newton per square meter is called Pascal, okay. So Pascal is basically, you can say, unit of stress, okay. And already we have mentioned that the kilopascal, megapascal, and gigapascal are bigger units of stress. So this was regarding normal. Now you can think of another type of force which we call shear force, okay. So basically in this slide you can say on the left side, okay, there is again section which is, or you can say plane, XY plane, but the load you can see, okay, the load is acting parallel to the section. So whenever a load is acting parallel to a section, so that type of load you will call shear force, okay, shear force. And here it is written shear force acts parallel to the plane, already you can see, okay. And second bullet says pair of oppositely directed forces will produce twisting, which you can call moment, which is shown in figure 2b. Here is, okay. So basically if you look into the top, okay, so this is top section, yeah, you can say top surface, bottom surface. So top and bottom, they are subjected to forces equal and opposite, okay. Similarly, if you look into right surface and left surface, oh, so they both are subjected to forces which are shear forces, okay, and they are equal in magnitude and they are opposite in direction. So basically, the top surface and the bottom surface which are having shear forces, you can see these forces are parallel to one another, they are equal in magnitude, and they are opposite in direction. So this will produce a twist which you call torque or moment, torsion, okay. So this twist which is produced because of this torque will tend to rotate the body in clockwise direction, okay. But there will be a resistive, let's say this is the applied torque, okay, because of this top and bottom forces. So this applied or external torque will try to rotate the body in clockwise direction. But the body doesn't want to rotate. So there should be some resistive twist or resistive moment from within the body, and that is given by the force which is on the left and the force which is on the right. So again, you can look into, okay, this is another set of two forces. They are equal in magnitude, they are opposite in direction, and they are also parallel, okay, to one another. So this will be a resistive couple which will be produced from within the body, and this direction is opposite to the applied one, the external one, okay, because it is in anti-clockwise. So basically this torque will tend to balance the body, okay. It doesn't rotate in direction in which the applied torque want to rotate the body. So this is another example in XY plane, that for example, whenever there are forces and they are acting parallel to the sections or faces, so what will they do? They will produce a couple, okay. And again in couple, like in force we mentioned, okay, there is external force, and whenever there is external force on a body, so there should be internal force from within the body. So same is the case here, okay. If there is external moment because of these forces, so there should be internal moment from within the body, because moment is also what? A type of force. So this shear force is a force which is causing a stress which is called shear stress. Okay, like in previous case we mentioned, when force applied is normal, then this normal force will produce normal stress, and that normal stress will be represented by sigma. Here you can see, okay, here you can see basically this body AB. Okay, this body AB you can see. So this body AB is subjected to forces P and P bar. Okay, so if you look into basically the load, so this load, what you will call this load? Anybody who can tell me what is the right terminology you can use for this load, P or P bar? Student, over to you. There were a number of different types of load we have mentioned in the first lecture during face-to-face teaching. Okay, so I have mentioned a proper name for this load. Okay, this load is acting. This load is acting perpendicular to axis of the body. You can see. Okay, AB is the body, and this body AB has got this axis. Okay, and the load is acting perpendicular to axis of the body. So what this load P you will call?
Sir, exactly.
Normal load.
Sir, normal
No,
load. Normal load.
no, it is not.
Axial load.
No.
Axial load.
Transverse. You remember? Transverse load. When a load is
Yes.
acting normal to axis of a body, so that load is called transverse load. Okay. So in this case, if you look into P or you look into P bar, so basically they are acting to perpendicular to the axis of this body AB. So this type of forces are called shearing forces, okay, or shear forces. Now, if you remember what I have mentioned in the face-to-face teaching, that basically if you want to analyze a body for the sake of stress determination, then one of the requirement is you will have to pass a cutting plane. You remember? So this part B, the middle figure is showing a line. Okay, so this line is basically a cutting plane. Okay, or you can say it is a cutter. So with the help of this cutter, you want to cut this body. So when you cut this body, so you will be having two parts of the body. One will be the left side of the body, one will be the right side of the body. Okay, so this is one of the requirement. And then the second requirement is then you can consider either the left side part of the body or the right side part of the body for the sake of determination of stress. Okay, so let's say you want to consider the left side part. Okay, so once you decide the left side part, then the second requirement is, or the third requirement is, you will have to draw a free body diagram of that part you consider. Okay, so this is the bottom figure you can see. Okay, AC. So AC is the left side of the body. Okay, after cutting. So this is called the free body diagram, and I have given a simple definition of free body diagram, that basically you draw the part in isolation with all the forces acting on that part, whether the forces are known or not known. So this is a simple definition of free body diagram. Okay, so basically if you look into the cut portion, okay, here we have cut, and then this part we have isolated. So it is very much obvious, okay, that there is a force P bar and there is force P, and these are the two forces which are acting on part AC. So here already in the lecture I have explained in face-to-face teaching, but again I just want to know your response. What is the difference between P bar and P? Students, over to you.
Sir, one is external load and the other one is the internal.
A little loud, please, little loud, so that everybody can hear properly. What is
Sir,
the difference?
Sir, one is external load and the other one is internal load.
Yeah, you are right, but this is not the right answer. The right answer, I will expect that you should name both the forces. You should say P bar is the external applied load on the body, and P is the resistive force. Okay, P is the resistive force. Okay, because when you say one is the applied and one is resistive, then it is not clear which one is the applied one and which one is the resistive one. Okay, so for sure this is the external applied load, which is P bar. Now when P bar is transverse, so resistive force should also be transverse. Okay, this is confirmed. Like in case of normal load, when applied external load on a body is acting normally, it is normal load, then the resistance from body, the internal force from body, okay, the reaction from the body should also be normal force. Okay, in this case, okay, when the applied load is transverse, it is acting vertically upward, so the resistive force must be acting vertically down. Why? Because another requirement for determination of stress or stress analysis is that we must ensure the body we want to analyze is in the state of equilibrium, meaning you will have to apply equilibrium condition. So here the equilibrium condition, which is sum of the forces acting along y equal to 0, you will apply sum of forces along y. So how many forces along y? 2, p bar and p. So these forces should be equal in magnitude and opposite in direction. Only then it is possible when the body is in the state of equilibrium. Okay. So here, okay, now again, what is the definition of stress? So the stress we define is load per area. Load per area. So area is from the cross section. Okay. The shape of the cross section will be given. So using the dimension, you can calculate the area. And here is P. So remember, whatever load is appearing in the definition of stress, so that load will be resistive load. Okay, it is P, and it is shown here. Okay, at the cross section P. But this P you can put equal to P bar. Why you can put equal to P bar? Because already I mentioned that you will have to apply equilibrium condition, and according to equilibrium condition, sum of forces along y equal to 0 is giving you P equal to P bar. So this is how you can calculate or you can analyze the body for determination of the second type of stress, which is called shear stress. And remember, the symbol is tau, T-A-U, tau, which is again a Greek letter. So this is a symbol we have reserved for shear stress. Okay, so just little extension of this previous concept. Again, I want to define normal stress, how you can find out, and shear stress, how can you find out? Okay, but little extension of the previous. Okay, so here again there are 3 figures on the slide. You can see part A, part B, and part C. So remember, student, this is very much important. Okay, so every student should be very much attentive. Okay, very much attentive. Now in this figure A, which is on the extreme left, okay, you can see a body. Okay, this is an arbitrary body. Okay, body of some arbitrary shape. Okay, we will consider, and you can look up these forces. Okay, this is F1, F2, F3, F4. So the body, the solid body, is subjected to external forces. Okay, so if you remember in the lecture, I have mentioned that once there is a solid body and that solid body is subjected to external forces, only then it will be your duty to look into the body, to analyze the body for the determination of either stresses or strain. Okay, so now it is the case. You can see here there is a solid body and the solid body is subjected to external forces. Okay, so now you can play your role as a student of mechanics of material. Okay, to know what is the stress or the stresses which are produced in this body because of the applied loads. Okay, so one of the important requirement is that, for like in previous slide I mentioned, that basically stress we define at a point. So if you want to analyze the stress or determine stress, so you will have to decide, okay, the point. So here the point we select is point Q. And then second requirement is you will have to pass a cutting plane through point Q. So this dotted you can show, okay, you can see. So basically this is the shape, or this is the portion, or this is the section of the body which you will expose after you pass a cutter through point Q. So again you will divide the body, okay, into 2 parts. One will be the left side part, one will be the right side part. So let us consider the left side part. So this left side part you can see in figure B. What is figure B? Nothing except the left hand side part of the body after cutting the body by a cutter, by a cutting plane, when it is passed through point Q. Now here you can see, okay, with the left side, this is the external force associated, this is the external force associated, okay, and this section you can see, okay, this light, you can say light dark section, okay, so this section is basically called cross section. This you will call cross section. Why? Because you have cut the body, and this is the section, or this is the plane, okay, or this is the face of the body which is exposed, okay, which is exposed. So here again in previous case, you remember what we did? We consider a small differential element, okay, of small differential area del A. So same is the condition here, okay. So things are the same. Once you understand lecture 1, or so those things are propagating in onward lectures, okay, or something you understand in lecture 2 properly, clearly, precisely, concisely, those things will propagate in onward lectures, okay. So you can correlate these topics or these explanation with previous slide, okay, what we considered for stresses. So same type of thing, point, and then cutting plane, and then cross section, and then differential element, and then differential area, and then differential force, everything same, everything same. So here what we want to do, basically we want to go for 3D, okay, three-dimensional analysis. So we consider this is x-axis horizontal, vertical is y-axis, and the third is z-axis. So what we here do, this small rectangle from figure B, which is the differential element, we want to take and we want to show it little exaggerated, okay, enlarged. We want to zoom in for clarity, okay. So this is the differential element which we have taken from the cross section. So it is again having the same del A, the area, and the resultant force del F, okay. This is the force. So this force we split into component. So one is the component of the force along X, one is the component of the force along Y, and one is component of the force along Z. So basically the resultant force del A we have split into its components, and the components we have considered along X, Y, and Z. Now again the previous explanation that whenever there is a force and the force is acting on a section, so the force may be either acting normal or it may be acting parallel. So this is the same explanation we will go for. Already we discussed in previous lecture, previous slide. So here if you look into this situation, which is part or figure C, so you can see this del Fx is a force which is normal to the section, okay. So when this is normal force, so this normal force will give you normal stress, which you will represent by sigma. And if you look into this vertical force del Fy, so it is acting parallel to the section or surface, so it will give you shear force because it is shear load, for the reason it is acting along the cross section. Similarly, the force which is del Fz, it is also acting parallel to the section, so this will also give you shear stress, okay. So basically one is normal force and two are shear forces. Therefore, using the previous definition of stress, okay, you can say that the del Fx, which is the normal force, okay, it is giving you normal stress, which we represent by sigma x, because it is the stress which is acting along x-axis, okay. And the force which is del Fy is giving you tau xy. So basically this x means x phase and this y means y direction. Basically shear stress on x phase in y direction. This is the way you will pronounce this, okay, or you will describe this, okay. Similarly, the third force or component of force along z, so this is also parallel, and when it is parallel, so it is also giving you tau xz, which is shear stress, okay. So again in this case x is the phase because it is common phase. You look into this, okay. So this this cross section or this face is common, okay. So let's say this is x, and because it is perpendicular to x-axis, so when it is face x, so on this face x there is the three forces. One force is acting in x, one is acting along y, and one is acting along z. Therefore here is x, okay, common. So here you can also put another x, so it will be, or it could be sigma x, meaning normal stress on x phase in x direction. Here you can say shear stress on x phase in y direction, and this you will call shear stress on x phase in z direction. So out of three, for the x phase you can see one is the normal stress and one is the shear stress. Now little example, little more explanation for shear, some example, okay, where could be, for example, or here where you can expect the shear stress, okay. So these on the slide you can see a simple joints, okay. So basically nut bolt arrangement is used to join two member, okay. So there is a body A, you can see, okay, body A and body B, okay, and these two bodies are connected together with the help of a nut bolt arrangement, okay. So when this joint or this connection is subjected to force, so again if you look into the direction of force, this F and this F bar, okay. So basically again you can see the bolt is having the axis, okay, which will be along y axis, and to this axis of the bolt you can see the forces are acting normal, okay, perpendicular. So therefore the forces you can call transverse forces, okay. So in this case we call it is a case of shear, single shear. Why single shear? Because basically if you want to open the joint, so there is at one point if you pass a cutting plane, okay. So let's say you cut the bolt, okay, at this point by a single cutting plane, okay. So if you just pass a single cutting plane and that cutting plane will cut the bolt at this, so you can think of the connection will be open, okay, this will be open. So only one cutting plane you need, and when you cut the bolt by this cutting plane which is E bar, so again the same explanation, you will be having top portion of the bolt you will be having bottom portion of the bolt, and any one of the two portions are part of the bolt you can consider for stress. Okay, so here if you look into the top part of the bolt is considered. Okay, so again here is F, the external applied load, and this P is the resistive force. Okay, and since F is acting along x-axis, therefore it is understood P, or the resistive force, must be acting opposite to F to balance the effect of this one. Okay, so here again P is the resistive force. Why resistive force? Because P is acting at the cut section. Okay, so whatever is acting at the cut section, that will be resistive force. Okay, or maybe sometime a resistive moment. Okay, so basically again using the equilibrium condition, you will say sum of all the forces acting on this body along x-axis equal to 0. So that will give you P equal to F. So here is the simple definition of shear stress. Since load is shear, so it will give you shear stress, and that is equal to shear load, which is P divided by A. But here there you can see P, you can put equal to F. It will be F by A. Why P equal to F? By simple discussion that equilibrium condition says sum of forces along x equal to 0. So that will give you F equal to P, right? This is again another connection or joint where two bolts are put, okay, to connect some parts, maybe part A, B, C, D. Okay, so here it will be a case of double shear. Why double shear? Because in this case, for example, if you want to open the joint, so only one cutting plane is not enough. If you look into, let's say, this bolt H, the right side bolt. Okay, if you think, okay, I pass a cutting plane here. Okay, so I cannot open the joint because it is still connected here. Okay, so, but if I also cut the bolt at this, okay, so one cutter I will pass here and one cutter I will pass here. Okay, you can see here also again. Okay, it is very much clear from his. So this is the bolt, and the bolt is something we want to analyze for the sake of stresses. Okay, that because of the applied load, what are the stresses which are produced in this bolt. Okay, so basically this is one cutter, which is a cutting plane K bar, and this is another cutting plane L bar. Okay, so then, okay, when you cut, then you can, let's say, consider this middle part. Okay, so on the middle part you can see, okay, what is F? F is basically the external applied load, and this is P, which is at this cut section. This is the resistive force, and this is another P, which is also acting at the other cut section, which is resistive force. So basically P and P, they are called resistive forces. Why resistive? Because they are acting at the cutting cut section of the body, and F is the external applied load. So here again you will have to apply the equilibrium condition, and you can see very simple, when you apply sum of the forces acting along x equal to 0, so it will give you F equal to 2 times P, or you can say P equal to F divided by 2. The simple definition of stress, already we know stress equal to resistive force by area, but here we can see that the resistive force from this figure is P equal to F by 2. So for P we put its value, which is F by 2, and we bring area here. So this is the shear stress which you can calculate, which will be produced in this case. So in single shear, this is the shear stress. In double shear, this is the shear stress. So some more explanation I gave so that it is clear to you what is the way of sectioning a body, what is the way of considering any part of the body, what is the way to make a free body diagram of a body, and then what is the way, for example, to put the body in state of equilibrium. Okay, and then you apply the formula, the equation of the shear or normal stress. Okay, and then you will get, okay, what is the so here, for example, this is the external load, and this will be given for sure because this is the external applied load, and you must be given, okay, an area from the dimension of the body. You can calculate. It is a bolt, and bolt is made of a circular cross section. Okay, receiving circular section or cross section. So dia will be given, or radius will be given. So it is very simple, okay, to put the value of the given external load and to put the value of the area. Area will be equal to pi r square, okay, for the bolt. Okay, r will be given, radius will be given. So very simply and very easily and very conveniently you can calculate the stress or the shear stress in these cases which are produced in the bolt. Again, this is again very much important. Again, this is same discussion what already I made with respect to determination of stress, maybe normal, maybe shear. Okay, so this is basically, you can again see this is the body. Okay, this what type of color, you can say maroon color or reddish color. Okay, so it's a body, and this is subjected to load. Okay, so basically this is called two force member. You can see the title, two force member. Why it is called two force member? There could be a three force member, there could be a two force member. So the simple definition of two force member is, you can see that when the body, in the figure you can see the body is subjected to forces, two forces. Okay, one is on the left side, one is on the right side, and the forces are collinear. Okay, and they are equal in magnitude, opposite in direction. Okay, so they become basically a component, or they become basically a member, which is called two force member. So in this case, you look into again, because basically this says the force which is acting normal to the section. Okay, so this force is normal force. Okay, and this is basically a cutting plane. This is what? A cutting plane. This light black color. Okay, so this is the cutter or the cutting plane. So when you cut the body, so again you consider the left part. So this is the external applied load, and this is the cut section or the cross section. And the cross section, what will happen? This will be the resistive force by the body. And whenever, okay, so this is basically the body or the free body diagram of the body in terms of forces. Okay, so this is the resistive force. The same body here we have put equal sign. Okay, so you can present this way. What is the difference between this and this? The difference is here on the cross section we have shown the resistive force, but in this case on the cross section or along the cross section we have shown the stress distribution. So basically, since the load is normal load, therefore you can see it is sigma. So sigma is normal stress. And again here we say, let's the assumption, the three assumption that load is passing along centroid and the material is homogeneous, and cross-sectional area you can see from the figure it is all the same throughout the length. Okay, so you can again see the same status or situation what we have seen in the previous slide, that each arrow or all the arrow are having the same length. Okay, so meaning this is the same stress which is acting along the cross section. Okay, so this is called uniform stress distribution. So again, if you look into the shear one, so this is the bolt already we have considered, and the light dark is a cutting plane. So when you cut the bolt again, okay, you consider, let's say, the bottom portion of the bolt. So this P bar is the external load, and P is the resistive. Why it is resistive? Because it is acting at the cross section. Okay, so now this is the cross section with the resistive force, but the same part we can show in this figure. Okay, and instead of showing the force on the cross section, but we show the corresponding stress. So here, what is the stress? You can see tau, and tau is for shear stress. Why it is shear stress? It is shear stress for the reason this load P, which is resistive force, it is acting parallel to the cross section. Therefore, it is shear force. When it is shear force, so the stress it will cause will be shear stress, and we will represent this shear stress by a symbol tau. And again, you can see from the direction. Okay, the direction. Okay, so each shear stress is acting parallel to the cross section. So this was all about the stresses, okay, whether normal stress or shear stress. In the beginning, you remember I mentioned that whenever a solid body you subject to external load, so there will be stress produced, or there will be strain, and there will be strain produced. So your duty, your responsibility, your job, your role would be to determine the stress and to determine the strain. Okay. So in the previous slide, so far what we discussed, we saw how can we analyze a given body for determination of stress, and you saw the stress may be a normal stress, the stress may be a shear stress. Okay. Now we want to go for the other quantity what I mentioned, which is called normal strain, which is called strain, because when you apply load to a body, so that will also produce strain. Now we want to know how can we calculate strain which will be produced in a solid body when the solid body is subjected to external load. So this is an example, and if you remember in the classroom, in face-to-face teaching we have discussed. Okay, and if you remember, I mentioned you just consider this body like the rod of the projector. You remember in the classroom there was a projector, okay, and the projector was supported by some rod, okay, and the top end of the rod was fastened to the ceiling, okay. So that was the case we mentioned that we can just consider, okay. And here is, for example, if there is no projector or no body attached to this bar, okay, or this rod, so there is no stress, there is no strain, okay. And let's say L is the initial or the original length of this body. But when you apply load, okay, let's say you attach the projector, okay, the multimedia to this rod, then what is P? P is basically the load of or the weight of the multimedia. Okay, so basically in this case you can think of the rod is subjected to this P due to the load or the weight of the projector. So when you apply load, so because of that load, this body, since this load is normal, again you think of the load, okay, this load is acting normal to the cross section. You can see, okay, this is the cross section, okay, or this is the section, and load is normal. So, and again, when it is normal, so in normal it is tensile force because the direction of the load is away from the section or face. So what is the effect of this load? The effect of this load will be, it will tend to elongate elongate, and you can see the body length has increased. Okay, so let's say final length is LF. Okay, so when you subtract the initial length from final length, then you can say this symbol, which is, let's say, delta. This is the change in length. Change in length. Okay, so basically, again, when there is normal load, you have seen the stress is normal, and when stress is normal or load is normal, so strain will be normal. Okay, so like in case of stresses, you saw the stress could be a normal, stress could be shear. When load is normal, stress will be normal. When load is shear, stress will be shear. Same is true here. Okay, when load is normal, strain will be normal, and when load is shear load, the corresponding strain will be shear strain. So at the present slide, we are talking about normal strain. And in the figure, you can see the load applied to the body is normal load. It is acting perpendicular to the face or section. And the effect is, it is elongating. So here the effect of load is to bring change in dimension. Okay, to bring change in dimension. So initially it was L, and now the length is increased from L. Okay, so this you can call change in dimension. So some symbol already you can see P is the axial load of the normal load. Okay, it is also axial load because it is acting along axis of the body, and it is also normal for the reason it is acting normal to the face. A is the cross-sectional area of the body. L is the original length or initial length before load is applied, and this symbol is the change in length. Okay, so the simple definition mathematically you can write that normal strain will be equal to a change in length divided by original length. So this epsilon, remember epsilon is a symbol, again Greek letter, which is reserved for normal strength. So in numerator it is length, and denominator it is length. So length divided by length, it is INF less quantity. Okay, so basically you can see stress is a dimensionless, it is a dimensionless quantity, since it is the ratio of two lengths. But you remember we have mentioned that it is common practice, it will be good to state it as the ratio of two length units. For example, you can put it meter per meter or mm by mm, or you can put it inch per inch, so that people will know it is strain. Okay, it is strain. So shear strain, what I remember mentioned that when load is stress is shear stress. Okay, so that will cause shear strain. Okay, and you can see here. Okay, in this top figure. So basically, the symbol you can see on the right face. Okay, it is star. Similarly, on the left face it is star. Okay, on the top face it is star. On the bottom face it is star. Okay, so basically it is a small cube differential element in 3D. Okay, so it's like a cube. Okay, and you can see like in previous case. Okay, I mentioned that the right and the left. Okay, so these are the forces or the stresses which give a couple. Okay, and this couple would like to rotate the body in anti-clockwise. Okay, but this top one and this bottom one is another couple. Okay, because stresses top and bottom should be same, directions are opposite, and they are parallel. Okay, so this is giving another couple. Okay, so and again if you look into this top or this top, so look into every top, it is basically acting parallel to the face. Okay, it is not normal. So when it is acting parallel to the face, so it means it is because of a load which is acting parallel to the face. Okay, so such a load or such a stress will produce strain in the body, and that strain we call shear strain. Okay, but remember here I have mentioned, okay, that shear stress is acting on an element of material or accompanied by shear strain. This already I mentioned. What is important? You note the shear stresses have no tendency to elongate or shorten the element. Remember, shear stress job is not either to elongate or to shorten a body to which it is acting. It is only normal stress. When load is normal, so the normal load will either bring change in length, whether the length will be either shortened if it is compressive load, or the length will be short. Okay, it is elongated if it is tensile load. In this case, okay, whenever this is that in normal load, when the direction is tensile, it is the tensile load. Then what is the effect? It is elongating the member. But if you think this load will reverse, okay, it will become the compressive load, and in that case, basically the load will tend to shorten the member. Okay, so basically in this case, what is the effect of the load? It is bringing change in dimension. Okay, change in length. But here shear stress is not, since shear stress is parallel, it is not perpendicular to face, so it is neither bringing elongation nor shortening. Okay, what it is causing, so basically it is bringing change in shape of the element or of the body to which the stresses are acting. And you can see in this figure B, okay, the middle one, This is basically the original shape of the body, okay? And then once the loads, the shear loads or shear stresses were applied to the body, then they will, since they are acting, okay, parallel. So because of this, okay, this is basically you can say that distorted shape, okay? So there is change in shape. This is the original and this is the final. So shear stress is bringing change in shape. And again, you can look into this dimension in the classroom in quite detail. We will explain, okay? Or you can come to this one, the bottom one. Basically, it is in XY, okay? In XY. So basically, original side is, let's say you consider this side, okay? This side, okay, which is originally vertical, but after you applied shear loads, it will tilt to the right, okay? So this is the final, okay? So in between there will be some angle, okay? And that angle we call gamma, and that gamma is basically a symbol for shear strain, okay? So basically you can see this dimension, which is del S. So basically del S means from this point, which was the original position of the side then because of shear load moved to the new position, okay, to this point. So this is the linear length, okay, which is covered. So this is a small right angle triangle. You can see the small right angle triangle, okay, you can see, and this is length of this side, okay, the side we have considered. So when you apply tan of theta to this right angle triangle, then you can say tan of theta will be equal to this perpendicular, which is delta S divided by this base, okay. So this is basically this one. And then from mathematics rule, you remember, then if angle is very, very small, then tan of angle will be equal to angle itself. So in this case, how we can say that, for example, then gamma equal to this del S by L. So this is how we can calculate shear strain. A simple quantity, important quantity, already we have discussed in today's lecture overview of the same. This is called Poisson's ratio. So the name shows it is a ratio. It is having no unit, okay? And Poisson, the person who basically introduced or presented this ratio, okay? That's why it's called Poisson's ratio. So again, my dear student, if you look into the figure, so nothing new. Already from slide 3rd, 4th, or 5th, okay, of today's lecture, what we have discussed, okay, that there should be a solid body. So you can see a solid body, and that solid body is subjected to the load. You can see this is the load acting to the solid body, and this load is then normal because it is acting normal to the face, okay. So everything is the same, and whenever there is load acting on a body, so this load will produce stress. So you can see stress, okay, sigma. Since load is normal, so we can use the symbol sigma, okay. And whenever there is load, so that load will also produce strain. Since load is normal, therefore strain will be normal, because strain normal will be represented by a symbol epsilon. But here important is when you look into stresses, so stress you can see in x direction. Let's say, okay, this is the x-axis, okay, along which load is applied. So load is applied to the body along x-axis. This is the y-axis, which is perpendicular to x-axis, and this is the z-axis, which is perpendicular to x and y-axis, okay. Now, since load is acting along x, therefore stress will be along x. So along x, stress is not zero; it is there, and you can calculate. How can you calculate? This load will be given, okay. So you divide this load by this cross-sectional area A. So this will be sigma x equal to P by A, okay. So you can say normal stress along x is not zero, but normal stress along y and along z is zero. Why it is zero? For the reason you can see in the figure, along y-axis or along z-axis there is no load. If there is no load, so there will be no stress. Very simple, because stress equal to load by area. No load, no stress. But if you look into strain, so strain, although stress and along y and along z is zero, but strain in the body along y and along z is not zero. And you can see from the figure, okay. If you look into, okay, this is the stress state, a state of stress along, you can see here, okay, here is the stress, sigma x equal to P by A, okay, along x, okay, along y, no stress because no load, along z, no stress because no load, okay. If you look into the bottom figure, which is part C or figure C, so here you can see, okay, basically the dotted position shows the original position, okay, the dotted dimensions, okay, shows the original position of the body. And after the body is subjected to load, then since the load is, you can see the load is tensile, so what it will do? It will increase the length of the body. Okay, so you can see in part C, okay, length of the body is increased, okay, because of the tensile load. But this increase in length of the body is because of decrease in the width of the body and decrease in in thickness of the body. Okay, so let's say this is thickness and this is width. So width you can see, okay, width is taken along z-axis, okay, and this thickness is taken along y-axis. Okay, so basically length is increased, which is along x, so dimension along x is increased, dimension along z is decreased, which is the width, and dimension along y is decreased, which is thickness. So what is the definition of Poisson ratio? It says, okay, the symbol which is used for Poisson ratio, it is mu, N-E-U, again Greek letter, okay. So this shows lateral strain divided by axial strain. Okay, axial strain means the strain which is along axis of the body. So basically, axis of the body is along x-axis, okay. So the load is acting along axis of the body, and the strain produced along axis is called axial strain, okay. And lateral strain, so lateral strain basically means the strain produced in a dimension which is perpendicular to axis. So basically, you can see here, okay, this is axis of the body, which is along x-axis, okay. So to x-axis, y is perpendicular. So this dimension along y, which is thickness, is called lateral dimension, okay. And this is also perpendicular to x-axis, okay. So this dimension, which is the width of the body, you will also call lateral dimension, okay. So when change is happening along a lateral dimension, maybe z-axis or maybe y-axis, so that will bring lateral strain, okay. So here we say Poisson ratio equal to lateral strain divided by axial strain. So if you consider xy plane, so it will be epsilon y by epsilon x, okay. Or if you look into z and x, so it will be epsilon z divided by epsilon x, okay. And you can put, okay, in the numerator minus. Why? Because along y or along z, the dimension is decreasing, okay. But along x, the dimension, which is length of the body, is increasing. So that's why we put a negative sign to show that when the length is increasing, so there is decrease in the other dimension, okay, which may be the thickness or which may be the what is called width of the body in case of this rectangular shaped body. So this quantity, it is a material property, and for different material, it is having its own value. For example, here you can see that it is roughly equal to 0.33 for metals, and it is 0.25 for ceramics. Somehow for other, maybe you can see, okay, here is the polymers. So the value is given roughly equal to 0.4. So from table, because when materials are given, you can go to the table, and from table, you can take the Poisson ratio for a given material. Okay, so if you have any question, better you ask a question. We will take then some break, maybe let's say 5 minutes break, okay, before we start the second lecture, okay. So over to you, student. Anything you want to ask with respect to what we already discussed? Now you can open your mic, unmute your mic.
नो सर, सही हो गया, समझ आ गई.
No, sir, it's all right.
Okay, so then let's go for a 5 minutes break, okay, and then inshallah after 5 minutes we will start again, right? So that there is some.
Yes, sir.
Raj,
Yes,
Okay,
sir.
so
Yes, sir.
let's
Yes, sir.
you can see. I want to maximize the slides, okay. So is it there? Lectures are there. The slide you can see on the screen.
yes, sir.
Okay, good.
Yes, sir.
Good. Very good. Okay, Shabas. Okay, so second part, and in this again, what I have mentioned in the classroom today, in the beginning I mentioned that for every lecture, it is important in the beginning of the lecture, you must know what is something we are expected from this particular lecture to have a clear-cut understanding of. Okay, so in this case, I would like to mention the learning outcome. For this part, you can see on the slide, and this is you at the end of this lecture or part of lecture should be able to describe Hooke's law. And then second, you should be in the position to discuss stress-strain relationship. And then you are expected to be able to be in the position to be capable of drawing and explaining stress-strain diagram. So this was the diagram and the relationship again during face-to-face teaching in detail. In more detail we have covered, just an overview. So here a question may arise why we want to go for knowing the stress-strain diagram, okay, or the stress-strain relationship, okay. So basically some theory you should look into. structural analysis and design. Basically, if you want to analyze a structure, like I mentioned in the beginning, a structure or maybe a machine element, you can analyze, let's say for the sake of stress, okay, that what are the stresses produced in the structure or machine element. So that is called stress analysis, okay. So whether it is a matter of analysis or structural analysis, or it is a matter of design, okay. You remember in the beginning I have mentioned in the classroom that basically this subject is a prerequisite. It is something very important for your two subjects in semester 4 and semester 5, which are called design of machine elements, okay. And the more rightly you understand the topics, the concept, the fundamental, the theory of this mechanics of material, the more rightly you can understand, or you will understand the concept of the design, okay. So basically, already I have mentioned in the class, design, basically, if for example you want to say that I want to design something, let's say you want to say I want to design a chair. So what is the minimum requirement in design, okay? In design, basically the minimum requirement is that for the chair, okay, which you want to design, if you come up with the suitable dimension of the chair or the parts of chair, because chair is made of parts, okay, there are legs, okay, and there is the seat you sit on, and there is a support, okay. So there are different parts of the chair, okay. So when you come up with suitable or appropriate dimension of the chair, and at the same time you also decide the appropriate or suitable material for the chair, then you can say I have designed a chair. Or it may be, for example, bearing, or it may be shaft, okay, in machine elements. So once you decide, once you conclude, once you come up with suitable dimension, maybe length, dia, maybe width, height, that type of thing, okay, and at the same time you also come up with suitable material, okay, this is the material I would like to use in fabrication, in manufacturing of this part, that is design, okay. So important is whether it is a matter of structural analysis or it is a matter of design. So in both cases, it is very much required, okay, that you must have understanding of the system of applied forces. In the beginning we mentioned, okay, force, axial force, normal force, and in normal force, compressive force, and then tensile force, and then shear force, okay. So this understanding of forces or system of forces, okay, because sometime in future you will see that a body or structure or machine element is subjected to a number of forces. There may be shear force acting on the body, there will be at the same time normal force acting on the body, at the same time there may be bending of the part, okay. So this is basically called system of applied forces. So one of the requirement is that you should have a good, a clear understanding of the system of external applied forces which are acting on the body, and at the same time you must also be aware, or you should understand, or you should be having understanding of the behavior of material, okay. So material behavior, material response, material reaction, okay. So this is important. So the behavior of material can be studied by means of mechanical testing, okay. Now in order to understand a clear-cut understanding of behavior or response of material, you need mechanical testing. What do we mean by behavior of material? Like you can say that when we apply external load to a material, then what is the way the material will respond? What is the way the material will behave in? So that behavior of the material, if you want to study, then the requirement is a mechanical testing, okay. So in mechanical testing, then there is a diagram which is called stress versus strain diagram. So they are quite often used to describe, to explain the material behavior, okay. And stress strain diagram are theoretically identical for the same material, but technically there is always some differences. Meaning, if you use the same material and you make a sample of that material and you conduct the tensile test and you draw a stress strain diagram out of the test data, and then you of the same material produce another sample, and then you again test this one, and from the test data you draw another stress strain diagram, then the meaning of this, the last bullet, is that theoretically we can say that basically this stress strain diagram will be similar, but technically they may be different little from one another. So basically, from mechanical testing, if you remember, we have mentioned that there is a requirement that you should prepare a sample, okay? And that sample you can see in the figure on the right side. So it is basically a sample which is subjected to tensile force. So in this case, the load is normal, and again it is tensile because the load direction is away from the the cross section. And on the sample, what you will do, so basically you will put two marks. You can see this is the top mark and this is the bottom mark. Okay, so in between these two marks, you want to measure the change in length. So this length, which you can see, which is taken from top mark to the bottom mark. So this length you will call gauge length. Okay, and in this length you want to measure the increase in length or change in length. Okay, because basically when you put or when you mount this sample in the UTM, which is universal testing machine. Okay, so basically then you apply the load. Okay, so the load is normal load, and the load we will apply gradual. Okay, from 0 up to maximum value. So basically when you apply load with the help of this machine, so this machine will elongate, okay, this sample, and there will be increase in the length. Okay, you can say change in the length. So the change in the length you would like to measure in this in between these two marks. Okay, in the gauge length. So this is the same explanation basically. So you can see again, this is the sample which is subjected to tensile load with the help of the machine. And let's say the original length of the specimen is L, and after it is subjected to load, so because of load there will be elongation. Okay, there will be elongation or change in length. Okay, which is shown here, okay, with the symbol delta. Right. Now, how to calculate stress and how to calculate strain already we have seen from previous lecture. Okay, the previous lecture or part of the lecture was with respect to how we can determine or calculate stress and how can we determine or calculate strain. So using those approaches, okay, you will calculate stress and you will calculate strain. Okay. Okay, so basically here you can see, okay, already I have mentioned the stress is calculated using the cross-sectional area. Okay, because cross-sectional area you can see, okay, you can calculate, okay, of the sample. Deformation, which you can see the dotted one, okay, this there. So from deformation, okay, you will calculate the what is called the displacement. Okay, and then using the displacement, the deformation, you in the original length you can calculate the strain. And there is another alternate way by using a strain gauge. Using a strain gauge, you can also measure the strain which will be produced in the pot when the pot is subjected to load. And then once you have calculated stress and you have calculated strain, then you draw a diagram which is called stress strain diagram, because you have got stress, you have got strain using the formula, the approaches we discussed in the first part of the lecture. Then once you have got stress and then also strain, and then plotting the data, the diagram you will obtain, that will be called stress strain diagram. Here, if you remember in the class when I was teaching, so I had mentioned that basically if you look into the test data, okay, when you are applying the load gradually, okay, from 0 to maximum value, okay, so for each load there will be information elongation. Let's say P1, so it will be elongation del 1. When it is increased to P2, so it will increase to more elongation del 2, and so on. For example, P3, so it will give you del 3, and so on. So basically, what is the test data? The test data you are getting in terms of load and corresponding elongation. So here I mentioned that why we don't draw a graph between the applied load and the corresponding elongation, which we can call load versus elongation graph. This was the question, if you remember, I asked. Okay. So the answer, if you know the answer, you can give me. Student, remember the answer? Why we don't this lab data or test data, which is load we are getting or we are applying, and then we are getting for each value of load its corresponding deformation or elongation, and then we can draw a graph between load and elongation, and this will be called load versus elongation graph. So over to you. Why we don't make use of this data to plot a graph? Why you want to plot a graph which is called stress strain diagram? Students, over to you. These are explained already in the classroom, okay? These were explained in the classroom, okay?
To understand the material properties.
Yeah, the
Yes, sir.
objective is for sure.
The behavior of the object, the behavior of the material we are using, sir. We want to study.
Yeah, right. The objective is to understand the behavior of material, okay? But the right answer is the behavior of material you can understand more clearly and more rightly and more you can say accurately from the stress strain diagram. Okay, you cannot understand the material properties or material behavior from a diagram which we can call load versus elongation diagram. Okay, so this
Yes,
is
sir.
the reason we convert the test data from load versus elongation to stress versus
Strain. Strain.
strain. Yeah, and you
Yes.
remember, you can see here in the figure. Okay, this is the load. Okay, you can see again where is the okay. You can see the figure. So the load you divide by area, so it will give you stress, because stress is load by area. And here is the elongation. Okay, and the elongation, when you divide by the original length, so it will give you strain. So this way you change. Okay, the data from load elongation to stress strain. Okay, and the diagram you get will be called stress strain diagram. This is the various stages. Okay, this is like a strength strain diagram in which you can see basically the specimen which is undergoing through various stages. Okay, and you can see basically, since it is the specimen which is subjected to tensile load, so you can see the load will increase the length. Okay, so here the length is increased, and at some point there will be necking. Okay, so basically it is not necking should be here, basically this one. Okay, so at
Yes.
certain point when there is decrease in the dia. Okay, so this is the necking. Okay, and then at this point the material will fracture. Okay, so okay, so
नेकिंग
basically
नेकिंग से पहले
yeah,
सर फ्रैक्चर करिएगा सर, या नेकिंग के बाद? मतलब नेकिंग वो
no,
पॉइंट.
after necking, no, after necking.
यस सर.
Basically necking is here. Okay, this is the necking. Okay, you can see the narrowing. Okay, basically
यस
the size gets narrowing. Okay,
यस सर.
except, okay, so you can say, okay, this is basically the, you can say, the start of the necking. Okay, and
यस.
then when you further go, so the size goes and decrease further, unless you can see here. Okay, the size is so thin. Okay, the dimension, the size, the dia is so thin that it can no longer sustain or support the applied load. So what will happen? For sure, fracture
फ्रैक्चर
or
हो.
failure of the body or something will take place. Okay,
यस सर.
so basically here is the explanation. Also later on you can look into, already in the class I have explained that I have put, okay, the question mark, why stress versus strain, why not load versus elongation, what I asked already. Okay, so these are the basic explanation. Okay, so basically if you look into force versus deformation or stress versus deformation, so basically you can, for the same data, get a number of curves. So you can see curve 1, curve 2, curve 3, but if you put all together in the stress and strain diagram, then all the three curves 1, 2, 3 will merge. Okay, so this will give you one curve. Okay, and from one curve you can get the properties of the material. So it is recommended, it is advisable that in order to understand or study the behavior or properties of material, one must go to draw a stress strain diagram. So this is basically the stressor diagram, and let's say here we have taken the material, ductile material. Okay, and you can see again in the figure. Okay, so here is again you can see the necking. Okay, because the nerving of the size at this point has started. Okay, you can see. So this is the necking, and after necking, what happens? You can see here the failure. Okay, so if this is a ductile material, for sure it will be necking there starting. Okay, but if it is not ductile material, so you cannot expect, okay, any necking. Okay, it will be a sudden fracture. Okay. So, and again, if you look into the failure ages, okay, we can look into, if it is a ductile material. So after failure, when you look into the ages, okay, the surfaces of this, okay, so you can say cup and cone. This is like a cup, and this is like a cone. Okay, so this is again cup and cone if the material is ductile. Okay, and this is the stress strain diagram for steel. Okay, carbon steel, or you can say low carbon steel, and which is a ductile material. Okay. So you can see there is yielding. Okay, there is yielding, you can see, and there is necking. Okay, so this is the necking. Okay, and this necking is shown in the graph. Okay, in the SN diagram. But here in the sample, this is the necking on the left side in part A of the figure. You can see. So in this figure again, if you look into, so this is the figure. Take okay. So along horizontal strain, along vertical stress. So a number of points in the classroom we have mentioned. Okay, these are various important points. You can study, you can see in the diagram. One point is called proportional limit. Okay, one point is called elastic limit. Next point is called yield point, and there you can think of another point which will be ultimate point. Okay, so basically initially, for example, when there is no load, so no strain. Okay, no stress, you will be at zero. But when you apply load, so load will bring stress, and it will bring strain. Okay, so then you are moving, okay, increasing the load, and stress is increased and strain is increased. So initially there will be a point. At that point you will call proportional limit, and that will be the point you can say up to that point, the stress will be directly related to strain. Okay, so that's why it is called a proportional limit. Okay, after you cross that point, then there will be a point that will be called elastic point. Okay, so elastic point already we have discussed is the point at which, for example, if you remove the applied load, then the material has got the tendency to regain its original dimension. Okay, and if you go and you cross the elastic limit, and after that you remove the applied load, then there is not a possibility that all the strain will be relieved. Some strain will be there. Okay, the material cannot regain its original position. So after you cross the elastic limit, then there is a point which is called yield point. Okay, and yield point is a point at which yielding will happen. Okay, so yielding means the material will give you more elongation or deformation with little load. Initially, if you look into the graph, initially you have to apply more load. Okay, to elongate the member. But once you have reached the yield point, so that is the point at which, compared to little load you will have to apply, and more deformation, elongation, the component or the sample will give. Okay, so the yield point. Okay, and then what is yield strength? So basically, yield strength is the stress which is corresponding to the yield point that will induce permanent set. Okay, so basically, if you can see here, if this is the yield point on the graph, so corresponding to this yield point, you can see sigma y. So sigma y is called yield stress, or you can call it yield strength. Why we call it yield strength? Because you remember we mentioned that when the stress value is maximum. Okay, so maximum stress value we call strength. Okay, so after this point, then there is another point which is called ultimate point. And ultimate, what the name shows, the highest value, or the highest point in the graph. Okay, so this is the highest point in the strain diagram, sorry, in the stress strain diagram. And corresponding to this highest or ultimate point, if you look into the stress, so it is written sigma u. So sigma for a normal stress and u for ultimate. So basically, the stress corresponding to ultimate point is called ultimate stress. Okay, or in other words, we can call it ultimate strength, because this stress have got its maximum value. Okay, and the maximum stress is called strength. Okay, since this stress is corresponding to ultimate point, therefore this will be called ultimate stress or ultimate strength. And after that, what happens? You can see that failure or rupture of the specimen or sample will happen. Okay, so here you can also, which already in the class I have explained, that basically from this point, after you have reached yield point, so after each point, then what happens? Yielding starts. Okay, and then you can see the curve is moving down. Okay, it is moving down, down, down. But here, what happens? Okay, you can see at this point the curve moves then up. Okay, and it is going up, up, and up to this extreme point. Okay, after which what happens? The curve is moving down. Okay, and this region. Okay, this region. Okay, is called what? Strain hardening. Okay, strain hardening. Okay, so after strain hardening, you can see what happens? Necking. Okay, and strain hardening again important. What I have explained in the lecture. That why it is happening and what is the effect of strain hardening. Okay, so basically here I have put some explanation for strain hardening apart from what I have mentioned in the classroom. So it is something which you can also call work hardening, or you can also call it cold working. Okay, so it is basically a process of making a metal harder and stronger through plastic deformation. Why plastic deformation? Because you have reached the yield point, and after yield point or at yield point, plastic deformation starts. Okay, it is taking place. So when a metal is plastically deformed, dislocations move and additional dislocations are generated. Okay, so the more dislocations within a material, the more they will interact and become pinned or tangent, meaning more dislocations. Okay, so with plastic deformation, what will happen? More and more dislocation will move in the material. Okay, they will take place in the material. So what will happen then? A stage will come when this dislocation will become saturated. Okay, they will make a wave type. Okay, they will make a wave type, and there will be a saturation point, and that will be the point that this wave of dislocation, or because of dislocation, will act as a shield. Okay, as a shield for further okay, what is called dislocation, because you can see it will then this shield, or you can say the saturation point, or you can say the wave of the dislocation will then decrease the mobility of dislocations. Okay, So no more dislocation will happen. Okay. And what will be the result? The result will be material strength will be increased. Okay. Since material strength is increased because of this process which is called strain hardening, so that's why you can see in the graph, okay, that basically once strain hardening start, then the curves move up. Why it moves up? Because strength of the material is increased. Since strength of the material is increased, therefore you will have to apply more load, okay, to fail, to fracture the part or the sample or the specimen. Okay, so basically this type of strengthening, you can see this type of strengthening of the material is often called cold working or work hardening. Why it is called cold working? The reason is given. It is called cold working for the reason the plastic deformation must occur at a temperature low enough that atoms cannot rearrange themselves. It is because of low temperature. The temperature is low enough that it doesn't allow the atoms to rearrange themselves. Okay, that's why it is called cold working. The opposite is hot working. Cold working, opposite is hot working. So when a metal is worked at higher temperature, it is called hot working, and the dislocation in this case will then rearrange and little strength is achieved. Okay, so this is how we can define the strain hardening. So remember previous diagram and specimen, they were for ductile material. In this case you can see, okay, this is a brittle material. So this is the diagram on the right side for brittle material, and you cannot see necking. Okay, there is no necking either in the figure of the sample or in the diagram. You cannot see any figure. Okay, any necking. Okay, again second point is, after failure, if you look into the surfaces of the failed surfaces, okay, so there is not cup and cone shape. Okay, they are just flat surfaces. Okay, why? Because they don't give, the brittle material doesn't give any reasonable or noticeable elongation when you apply external load to them. Okay, so you apply the load and you increase the load from 0 to maximum, and what will happen when the load has got its maximum value, then the material or the sample or the specimen will suddenly fracture. Okay, so no necking, no cup and cone. But in previous case you saw in the sample there was cup and cone and there was necking. Okay, in the graph you cannot see. So basically you start from 0 and then you apply load, and because of load stress is increased. When the load reaches its maximum value, where it will give you the ultimate strain. Okay, so at that point what will happen? Basically this material will fracture. Okay, so here important point is, we mention about two material in the classroom, we have already discussed. Okay, one ductile material and the other brittle material. So whenever you are designing something of ductile material, so there is the yield strength. Okay, I want to bring you here again, yield strength. Okay, so basically this is the yield strength sigma y. So this is the governing strength which will be used in the design of component made of ductile material. But if you want to make use of brittle material, then for brittle material, since there is no necking, there is no yielding, it is sudden fracture or rupture, which takes place is ultimate strength. So for brittle material, the governing strength in the design you will have to use, that is called ultimate strength. So these are two important things you should remember. Okay, and then we can mention the Hooke's law, or we can mention the relationship between stress and strain. So basically in the SN diagram, sorry, in the stress strain diagram, okay, already we mentioned about the elastic point, okay, or the elastic region. So basically this is the region at which, for example, stress is removed or stress is relieved once you have removed the load from the body. Okay, so you can say that up to elastic limit. Okay, proportional limit, elastic limit, they are close to each other. Okay, so basically you can say to elastic point or up to elastic point, the stress and strain, they are linearly related. Okay, meaning when you increase stress, strain will increase and vice versa. So what you can say, okay, the Hooke's law. So basically Hooke's law will give a relation between stress and strain. If it is normal loading, so it will be normal strain, and it will be normal stress and normal strain. So basically you can write stress directly proportional to strain, or you can say stress equal to some constant of proportionality times strain. So here in this case of normal loading, the constant of proportionality is basically Young's modulus, okay, which is material constant, okay. It is material constant, okay. If it is shear loading, so again Hooke's law will show that shear stress directly related to shear strain, or you can say shear stress equal to some constant of proportionality times shear strain. And in this case, the constant of proportionality is again a material constant, but in shear loading it is called shear modulus of elasticity. So basically this is Hooke's law, which gives the stress and strain relationship in case of normal loading. And this is what? This is again Hooke's law, which gives the stress and strain relationship in case of shear loading. And in both these equations, again, I want to mention that E, capital E, and capital G, they are material properties, okay? They are material constant, okay? And if you look into the unit of E, so here from this equation, you know that the unit of stress is Pascal, okay, or megapascal, let's say, and strain is unitless. So if strain is unitless, then what is the unit of modulus of elasticity? So modulus of elasticity has got the same unit. What is the unit of stress? In this case, also in this case. So E and G, which are material constant, you will express them in terms of the units of stress, which is kilopascal, maybe megapascal, maybe gigapascal. Okay, so already we mentioned about ductile and brittle material with respect to the what is called stress strain diagram, and with respect to the surfaces after they have failed. Okay, and the same we can see from this diagram. Okay, if you want to mention the elastic versus plastic behavior. So here this the stress and strain diagram you can see. Okay, so basically this is one curve. Okay, the red one you can see A, B, C, and then up to rupture. So this is loading. Okay, this arrow. The arrow is up, okay. So this is showing loading the diagram, loading the specimen. So you for a 0, you load and then you reach B and then you reach C and then you reach a point where rupture of the specimen takes place, okay. Here at point C, if you want to unload the specimen, so this arrow which is moving down, this basically shows the unloading of a sample, okay, meaning you remove the load, okay, meaning you remove the load. So here it is very much obvious and clear that, for example, elasticity and plasticity. Okay, let me read it out. Okay, so again the same already we have mentioned. So if the strain disappears when the stress is removed, the material is said to behave elastically. Already we have mentioned. The largest stress for which this occurs is called the elastic limit. Okay, and when the strain does not return to 0 after the stress or load is removed, the material is said to behave plastically. So elasticity, plasticity, okay. Right. So the same you can see here. Let's say you load the component, okay, the specimen, okay. You load the specimen, and let's say you reach at some point, and let's say the point we call elastic point, okay. But elastic point, let's say this point B shows elastic point, okay. But elastic point, if you remove the load, then you will move back to 0, Why? Because at elastic point, you remove the load, and because of this, the specimen is capable to regain its original dimension, or original position, and whatever strain was there in the specimen, that is relieved, because that was like a temporary strain, okay. So, but if you cross the elastic limit and you move onward, so let's say at this point, let's say this is yield point, let's say earlier to yield point, okay. So you unload the component, unload the specimen. So you cannot expect, okay, you shouldn't expect then you will move this way and the strain totally will be relieved and strain will be 0. No. Then after crossing the yield point, and then when you unload the component, what will happen? Then this is the way, okay. So basically you will reach at point D. So this much strain you can read from the diagram, okay. Basically corresponding to C, if you measure the total strain corresponding to C, this much is the total strain, okay. The total strain corresponding to point C. But after you have unloaded the component, so you reach at point D. So this much strain is relieved. This much strain is relieved because it was temporary. But this much strain it is not relieved. So it will stay, it will retain, it will be there, it will remain in the sample as a permanent strain, okay, and this will produce a permanent set in the body, okay, or in the component. Okay, so there is some effect of composition on the material, okay. You want to make it ductile or brittle, so there is one way, okay. So effect of composition is high alloy content will cause the steel to become ductile, okay, and this is again the stress strain diagram, and we can see at point A, okay, it is low alloy content. So at point A, if you measure the strain, it is less or very less compared to strain at point B, and then at point C it is more, and then at point D it is again more compared to previous low curve, and at point E it is the maximum. Why maximum? Because it is high alloy content which is added to the steel. So what is the point? The point is high alloy content is something which is causing the steel to become more ductile, and the diagram shows, because when more ductile, so meaning more elongation, okay, and more elongation means more strain. So point E is giving you maximum strain you can measure, okay. So this is why, because the steel has become more ductile. There is also some effect of temperature, and high temperature will cause the material to become ductile, okay, and the same is also apparent clear from this diagram. So 70 degrees, 750 degree, 840 degree, 930 degree F, okay. So if you look into the temperature when it is increasing, so you can see the strain is increased, okay. Why? Because the material has become more ductile, and more ductile means more elongation and more strain. There is some effect of loading also. Loading, you remember in the beginning we mentioned there could be tensile load, there could be compressive load acting on a body, and for body we discussed two types of material, maybe ductile material, maybe brittle material. Now, if it is ductile material, then for ductile material, tension and compression behavior are assumed to be the same. What is the meaning? Meaning that, let's say, strength, we are talking of strength of the ductile material. So strength of the ductile material in tension and compression is the same. What resistance a ductile material is offering to, in case of tension, the same it can offer in case of compression, okay. But if it is a case of brittle material, then the tension and compression behaviors are different, okay. So again, in terms of strength, if you talk, so you can say that for a brittle material, strength in compression is more compared to strength in tension. So this is the effect of loading direction, tension and compression. Okay, so now in this case, you can see on the slide what we want to do. Again, more or less same discussion. There is a solid body, you can see in the figure, and the solid body is subjected to tensile load. It has got initial length, and it is elongated by magnitude, by amount delta. Okay, so all previous discussion. But the only thing here we want to mention is in this slide we want to come up with a formula, with a mathematical expression that will lead us, that will help us to determine the value of elongation. So here in the slide you can see, okay, this is the elongation. Now this much elongation in the body has occurred due to the applied load. And my aim, my objective is to find out the magnitude, the value of this change in length or elongation. Now, making use of Hooke's law, we can develop, or there is a equation, a relation develop, okay, which will give you the value of this change in elongation or change in length. Sorry. Already we know that stress is, because it is normal load, so stress will be normal, and similarly strain will be normal. So stress equal to load by area. Already we have seen. And strain, already we have seen that strain is equal to sorry, but this is okay. So from Hooke's law, this is basically Hooke's law, okay. This is the strain definition. And the strain, so you can write strain will be equal to change in length divided by original length, okay. And this is the Hooke's law, okay. The Hooke's law we mentioned that stress equal to strain time modulus of elasticity. So basically from this equation you can write, okay. From this equation you can write that this deformation equal to or elongation equal to strain time length, and then for strain, which is epsilon, okay, for this epsilon you can put this value, which is sigma by E, so it will give you this relation, okay. And again, for sigma, which is normal stress, you know this formula, okay? So you put P by A for sigma, and then you will get this expression. So basically, the change in length will be equal to P multiplied with L divided by product of E and A. And all the quantities already you know, okay? What is E? Material constant, which is the modulus of elasticity, and it is the material constant which is used in normal loading. This is A, which is cross-sectional area. This is P, which is the normal load. In this case, it is tensile. You can see in the figure. L is the original length of the original length of the sample before load is applied. Epsilon is the normal strength produced in the sample or specimen, and sigma is the normal stress produced in the sample. So here in the numerical, already you have seen, okay, that some data will be given, and making use of the data and making use of this formula, then you can be in the position to find out this. Or maybe the data may be altered, and maybe from this given formula you can find out sometime maybe cross-sectional area, or sometime maybe length, etc. Okay. So remember, this formula is workable. This formula is valid when the cross-sectional area of the sample or specimen or body is uniform throughout the length. And this formula is also workable when the same load is applied, okay, and this body is made of the same material. But if you come across a bar which is a composite bar, you can say, meaning it is made of different sections, okay. So you can start from the right, okay. The right section has got least dia, which is CD, section CD, and then there is section BC, which has more dia compared to CD section, and then there is another section which is AB section, which has got the maximum dia. So from this figure you can see that basically size is changing from section to section. Therefore area will be changing, because area is something you calculate from dia, okay, size of the given. Similarly, if you look into the load, so section AB is subjected to different load, okay, 60 kilo psi, 60 kilo pound and 60 kilo pound. So here is one load which is acting on section AB. But when you look into section BC, so the magnitude of load is different. Similarly, if you look into section CD, so magnitude of load will be different. So load is changing from section to section. Length, if you look into length, is also length of this portion is different from this, and again this is different. So length is changing from section to section. Also area is changing from section to section, and maybe material for AB is different from BC, which may be different from section CD. Then you can make, for example, this formula, okay. So the same formula, but in the previous slide we have mentioned that delta equal to PL by EI. But since here load, length, maybe material and size are changing, therefore you will write PI LI divided by EI time AI sum, and I will start from 1 to n. So here basically I is a number of the section, okay. So how many section? 3 section. When you put I equal to 1, let's say you put I equal to AB, so you will be dealing with this, okay, with this section I equal to AB, that what is the elongation produced in this section, okay. You will calculate that one, so that will be delta AB. Then you can put, okay, I equal to BC, so that will give you elongation in this part, okay. Okay, so that will be delta BC, and then making use of the formula, you can consider this section, and then it will give you what is called delta CD, okay. And then you make sum of all the delta, okay, delta AB, delta BC, delta CD, so which will be sum, okay. So this is how you can calculate, okay. And this is something, this is not required, just for your explanation, okay, but it is not required in problem solution. This is enough, okay, because here the concern is, the aim is to calculate the elongation, okay. So you should know at least how we can calculate, how can we determine the magnitude, the value of elongation for a given bar when subjected to load, okay. But here what is seen, you can see AB, okay. So this AB section of the body is subjected to, you can see this is compressive load, okay. So here this is 0, which is a reference, okay, no load, a reference line. So we above 0 we take tension, okay, plus, and below 0 we take compression, which is minus, okay. So since AB section is under compression, so this PAB, which is basically the resistive force for section AB, it is since compressive, therefore you will draw below 0. Similarly, if you look into this BC, so this side of BC is subjected to tensile, and this side of BC is subjected to tensile. So basically, BC is under tension. Okay. So load which will be corresponding to section BC, we will call PBC. Okay, and that is since tensile, therefore we can write above the zero, above the reference line. If you look into CD, so here it is in this, because of this load and because of this load, section CD is put in compression. So the load which is corresponding to section CD we will call PCD, and since this is the section CD which is under compression, so the resistive force will be compressive load, and therefore we have taken it is drawn below the zero. Okay, below the zero because it is compressive. So with all this, this was all about the revision, the overview of the previous lectures, so that it is fresh, and from coming lecture, inshallah, you will be in the position, you will be capable to understand easily the other topics of the subject. Okay. So from my side, over, and now it's over to you people. Any question you want to ask? So most welcome. Students, over to you.
No sir, clear हो गया sir.
Okay.
Sir, can you please upload the 2 tutorials in Google Classroom, sir? For us,
Yeah, for
we
sure.
don't
Already I
have
have,
that.
okay. No worry, I will. Okay, I will. If I forgot, because every more or less every day we are having classes. Tomorrow I have 2 classes. Okay, 3 hours, and then again another class 2 hours, 3 hours. Sorry, total 6 hours. Okay. So inshallah, I will remember. I will upload. But
Okay,
somehow,
sir.
if I
Thank you,
forgot,
sir.
no worry. You can make me remind. Okay, I will upload. Okay, right?
Yes,
So
sir.
प्रीवियस
Yes,
लेक्चर्स
sir.
भी अपलोड कर दे प्रीवियस
जी
लेक्चर्स भी अपलोड कर दे